Hello and welcome. In this video, I'll go over traditional electromagnetism, both classical and in its tensor form. This will be a bit of a break from before where I was showing geometric algebra, but this will be a bit of a break before I show the simpler and more elegant formulation of electromagnetism within geometric algebra. This video can be watched on its own to understand the basics of electromagnetism, but if you're interested in seeing the application of geometric algebra in special relativity and electromagnetism, then I recommend watching the rest of the series as well. So let's get started. We're going to first talk about classical electromagnetism. So in classical electromagnetism, so in classical E and M, or another way is to say in traditional vector mechanics, you have Maxwell's equations. Maxwell's equations are elements of a set of four differential equations. So I'm just going to say this, it feels a little weird grammatically to say this, but is a set of four equations or four differential equations It's a set of four differential equations. The first is called Gauss's law. You've probably heard of Gauss before, one of the greatest physicist mathematicians. So you have Gauss's law, which is the divergence of the electric field, which is a vector field, is equal to 1 over the permittivity of free space constant, which is just called epsilon naught, times rho, which is the charge density. So this right here, this is charge density. The next law doesn't have a formal name, but when I went to college, it was called the no magnetic charge law. And, or maybe a more precise word is the no magnetic monopoles. So, no magnetic monopoles law. And this law says that the divergence of the vector field of the magnetic field is 0. Basically, it's saying that there is no such thing as a magnetic charge density. There's nothing there. Because while there's an electric charge density, there is no magnetic charge density. The third law is known as Faraday's law. Faraday was one of the greatest physicists or experimental physicists of all time, and he didn't like mathematics, so he did everything visually, and he discovered a bunch of stuff about electromagnetism without ever dealing with the mathematics. And that law is that the curl of the electric field is equal to the negative partial derivative with respect to time. So my notation here is that the partial with respect to time is equal just to the partial subscript t. So the curl of the electric field is equal to the negative time derivative of the magnetic field. That is Faraday's law. And the last law is called the Ampere, which if I could write my M's correctly, Ampere Maxwell law. It was originally discovered by Ampere, who was a French physicist, or might be French speaking, but in a French speaking country. Forgive me for not remembering that. I'm pretty sure French, Ampere. And then Maxwell discovered a fix to this equation, and so the equation is now known as the Ampere-Maxwell law. I'm bugged that I'm having second thoughts about whether Ampere is French because the name is French. It's giving me a crisis in my knowledge of history. But this law is the curl of the magnetic field is equal to the electric current density plus some more constants, then the change in time of the electric field. And these are Maxwell's equations. Now you can write these out in vacuum. So I will do this. Then increase that. So you can say that in vacuum, and in vacuum is a physics term for rho equals to 0, rho equal to 0, and J equal to 0. Basically, there are no charges, there is no current. So in vacuum, you have that the divergence of E is equal to 0. The divergence of B stays the same. It's also equal to 0. The divergence, or the curl of E, stays the same. And the curl of B loses the the current density term. So in vacuum, you have these corresponding equations. And these equations are used to derive the, in free space, the electromagnetic wave equation. Because if you think about it, this basically means that a changing electric field a changing electromagnetic field in space creates a changing magnetic field in time. Or even better yet, is to say that when a magnetic field changes in time, it changes the electric field. So the electric field then changes in time, which then generates a change in the magnetic field. And so this goes back and forth, and they chain together, and it creates a sustaining cycle, which therefore generates a wave, where you can have the electric field propagating out like this. So if I draw this straight line, oh, that's not very straight. So I draw this straight out line like this, and it's propagating in this direction. You can have the electric field, which is changing in time. It's oscillating. But then it causes the magnetic field also to oscillate, which I'm trying to remember. So the propagation direction is E cross B. So then it'd be like this. or depending upon the different phase shifts you have, these are at different frequencies and such. But the idea is that the changing magnetic or changing electric field creates a change in magnetic field, and as they keep changing, they keep going in and out and in and out, and it propagates and it continues indefinitely, and so it creates a wave. So we want to find this wave equation. Well, to do that, we first need to recall that, well, maybe some of you recall, I had to look it up because I didn't remember it. There is a product rule. There exists a product rule in vector mechanics. And this is one of the reasons why vector mechanics, while relatively easy to learn, is somewhat annoying to deal with, because when you deal with more complicated products, you end up with horrible, horrible looking equations like the one I'm about to write. So you end up with this product rule where you take the curl of some electric or some field, vector field A, and that ends up being equal to the gradient of the divergence of this vector field A minus the Laplacian of this field. Of a vector. And so you need to know this product rule to be able to derive the electromagnetic wave equation. So first, you take the curl of the electromagnetic or the electric field. Now, because of Faraday's law up here, this is the same as taking the curl of the change in time or negative change in time of B. This right here comes from this. So when you take the curl of this, you're taking the curl of this. So, but before we input this into this equation, I'm going to use this product rule. Well, because we're dealing with a vacuum, the divergence of E is 0. So this term will be 0. So you end up only with this. You end up only with the negative Laplacian of the electric field. And that is equal to the curl of the negative time derivative of B. Well, in classical mechanics, you can take the time derivative first, or you can take the curl first. Because in relativity you can't, but in classical mechanics you can. So, because we're in classical mechanics, take out this negative sign and this partial, and it becomes the curl of B. And in free space, so in a vacuum, it just becomes this equation. So you end up with negative partial of t mu naught epsilon naught E, which simplifies to negative mu naught epsilon naught partial with respect to t squared of the electric field. And this just becomes, well, I'll write it in blue so that it's stands out a little more. This becomes, because of there's a common negative sign here, and there's a negative sign here. This just becomes the Laplacian, bad triangle, the Laplacian of the electric field equal to, and then let's take this over here equal to mu naught epsilon naught time derivative squared of E. So that's what this is equal to. In general, for the wave equation, however, I will write it like this. I will move this to the other side, so it's a minus sign, which means that this is equal to 0. So this will just go there. Then I erase this. And this is what I write for the wave equation. And you can do the same exact thing. Can do same thing for B. I'm not going to just because it's pretty much doing the exact same thing done here. But you end up with the result that the, sorry, not 1. You end up with mu naught epsilon naught partial with respect to time squared of B minus the Laplacian of B is equal to 0. And these are the wave equations in classical mechanics. This is how light was initially predicted by Maxwell when he solved this equation. And how does it go at light speed? Well, it was the fact that there's another identity, 1 over c squared, and in wave equations, the coefficient in front of the time derivative is a 1 over velocity term, and because these are equal right here, you get that the velocity is traveling with a magnitude of c. And so that's how these wave equations go at light speed. And so to emphasize that fact, I'm going to just rewrite this 1 over c squared 1 over c squared. Now let's move on to tensor mechanics. So now in tensors, or using tensors, so with tensors, we deal with relativistic electromagnetism. So in this, there are some definitions that are made first. And they seem pretty abstract for someone who has not worked with them before. The first is the 4 position. So you get the 4 position. And that is defined as x superscript mu, where this is an Einstein notation. This is basically saying you're taking the sum. You're taking the sum of mu equal to 0 to up to 3 of x mu. This is what the Einstein notation is. But what is it representing? Well, you can say that it's representing, and I'll do this little dot here to show that it's a representation. It has the 0th component, a first component, second component, and a third component. And there's also something in tensor mechanics where you can have it subscript, where it's again a sum, but what this means is that you have the subscript here, but then you have a negative. You have a negative sign, or you have this right here. So 1, x2, x3, and the way that this is related up to x to the superscript of mu is x0 minus x1 minus x2 minus x3. And so you have these definitions of position, just one has a relative minus sign. Likewise, you can have what's called the four gradient. And the four gradient is just the partial with respect to the four position. And this is often rewritten just as the partial lowercase or subscript mu. And it's equal to, or it's represented by the partial derivative. I'll just do this. Partial derivative of x superscript 0, partial derivative with respect to x1, partial derivative with respect to x2, partial derivative with respect to x3. So you end up with this four gradient. There's also the for current, or rather for current density. And that is given by J superscript mu is equal to c, the speed of light, times rho, which is the electric charge density, and then Jx, Jy, Jz. Where right here, these are just the current densities that you would find from the traditional vector. But now it's all encoded in this. And let me put this dot there. Now you deal with the fields. So you have the field tensor. Field tensor, which is just a 4x4 matrix that deals with the electromagnetic field, both the electric components and the magnetic components. And this is written F superscript mu nu, where this is you're now summing over mu and nu independently of each other. And this is basically represented by a 4x4 matrix. It has zeros in the diagonal, and the electric field is written 1 over c Ex component, 1 over c Ey component, 1 over c Ez component. And then right here, you end up with negative of all of the components that I just wrote. And then in the center, you have bz minus by, bx minus bz, by minus bx. And this is called the field tensor. And you can think of these components here, the mu and nu, as giving you the index for elements in this matrix. So for example, if you're doing the 0 and 3, then you're looking at the 0th row and then the third column. So 0th column, first column, second column, third column. So 0, 3 would be this element here. And so as you sum over these all, you're just taking all of the elements out of this matrix. However, there's actually another tensor that is needed to demonstrate all of Maxwell's equations, and this tensor is called the dual tensor. I've seen some people call it the gauge tensor, but I prefer the term dual tensor. So G mu nu, and it pretty much has the same form as this, except you swap out where different things lie. So these will all go out here, and you end up with bx, by, bz, and then with, or you'd end up with this here. Oh, that's not what I wanted to do. This here. Oh, wait, hang on. Messed up this one. Let's go here, here, here. And then you get that there, that there, that there, 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 and there. And this is the dual tensor. Then you can express Maxwell's equations. Maxwell's equations are written as or rather I should say become mu f mu nu, or sorry, this is nu, is equal to mu naught j mu and partial nu g mu nu is equal to 0. So in the tensor formulation, Maxwell's equations reduce to a set of two tensor equations, and where you're taking derivatives with respect to components and then summing over those components to get different values of the either 0 or of the what's it called, the four current density. To get a little bit of an understanding of how this works, let's then derive all of the laws from all of Maxwell's equations from this. So the first one will be, of course, Gauss's law. And that law looks like this. So it's partial of F, the zeroth column, or zeroth row, sorry, and then the new columns, then partial with all of the new positions. And this being equal to mu naught J naught, or J0. And this just implies, so if you take the position, these components here, the zeroth row, and then the 0 component, and then 1, 2, 3, you end up with the partial of EX over the partial of X, partial X, plus partial of EY with respect to Y, plus partial of EZ with respect to Z. But then you get a constant out front. You get a 1 over C. And this is because of the 1 over C up here. And this is equal to mu naught C rho, because the zeroth component of J is C rho. And this just implies that the divergence of E is equal to, 1 over epsilon naught rho. How did I get the 1 over epsilon? Well, this C right here goes over, so you end up with a mu naught C squared, which is equal to 1 over mu naught epsilon naught. So these cancel out, and you end up with just 1 over epsilon naught, and that's where it goes. So that's Gauss's law. The no magnetic monopoles law, so NMML, is given by the partial of the dual field, the zeroth row, nu, and then partial x nu, and this being equal to 0. So this just implies that all of this, so I'm just going to copy this, but I'm going to insert the components for B is equal to 0, which is just saying the same thing as the divergence of B is equal to 0. So it's the same law. Now, let's look at the Ampère-Maxwell law, which is AML. This is given by F1 nu partial of x nu plus partial of F2 nu partial of x nu plus partial F3 nu partial x nu. This being equal to mu naught times J1 plus J2 plus J3. And now these are just the JX, JY, JZ components that you find up here. And these will give you the Ampère-Maxwell law, which is this one right here. The curl of B is equal to all of this. So I'm not going to expand all of these terms out, but I'll expand out this one so you can see how the Ampère-Maxwell law comes out of the expansion of these. So this right here is going to be, it's going to be negative 1c partial e of x over partial t plus partial of b z with respect to y minus partial of by with respect to z. And so you can see that if you did this for all of these components, you'd end up with the x, y, z components, so the change of time of the entire electromagnetic field, and you would get the curl of the magnetic field. And then you could just move this over to the other side, and this means that you would get the same law, which is that the curl of B is equal to mu naught J plus mu naught epsilon naught partial time of E. So you end up with the same Ampère-Maxwell law. And you do the exact same thing for the Faraday law. Now I'm not going to expand the terms like I did before, but I will write them. So it's the partial of g1 nu with respect to x nu plus partial of g2 nu with respect to, oh, that's a bad partial x nu plus partial g3 nu with respect to with respect to x nu, that being equal to 0. You can expand each of these terms just like you expanded these, except you're using the dual tensor for it. And when you expand that out, you'll end up just getting all of the components for the Faraday's law, which is the curl of E being negative change in time of B. Then, using this tensor formulation, how would we go about representing the wave equation? Well, the wave equation just becomes this. Wave equation the wave equation just becomes partial alpha f mu nu equal to 0. This will become the wave equation in vacuum. And you can see that it has a similar form where you have two derivatives essentially. Two derivatives. And then you have the fields equal to 0. And that would be the wave equation for the tensor formulation. In the next video, I will introduce the algebra of physical state, I will introduce the algebra of physical space formulation of electromagnetism and show how it's actually very simple. You can derive it very simply from Maxwell's laws, and it allows for an even better encoding of special relativity than tensor formulations.